Okie dokie. All right. So this word right here is orthonormal. Orthonormal. Ortho and then normal. So ortho means at right angles. And normal means length 1. And of course, you know what a basis is. This is a set of vectors which are both linearly independent in span. So an orthonormal basis for vector space V a finite dimensional vector space V is a basis so these vectors B1 through BKs are all linearly independent. They're linearly independent with one another, and they span all of V. So it's a basis such that each vector in B has length 1. Writing this out in symbols, we just say, writing this out in symbols, we just say bi dot bi equals 1. Remember, if I take a vector and I dot it with itself, I get the square of its length. So if its length is 1, then the square of its length is 1. So this is for all I between 1 and k. So the length of all the vectors in this basis are 1. And all the vectors are perpendicular to each other. And we know that vectors are perpendicular if their dot product is 0. So if I and j are not the same number, then bi dot bj equals 0. Oops. So you could write this or this. They mean exactly the same thing. And you could write this or this. They mean exactly the same thing. So for example, if V is three-dimensional, remember what that means. It means every basis for V has exactly 3 vectors. And this is an orthonormal basis for V. If, for capital V, I should say, if we want, I'm going to continue over here actually. We want all 3 vectors to have the same length. So B1, they all have length 1. B1 dot B1 is 1. B2 dot B2 is 1. So B1 has length 1. B2 has length 1. B3 has length 1. And we want the dot product of B1 and B2 to be 0. We want them to be perpendicular. B1 dot B2 is 0. We want B1 and B3 to be perpendicular. B1 dot B3 equals 0. And we want B2 and B3 to be perpendicular. B2 dot B3 is 0. I could just as easily go ahead and put B2 dot B1 is 0, but B1 dot B2 is the same as B2 dot B1, so it's not necessary to write these 3 down here. So these say that all vectors B1, B2, B3 have length 1, and these say that they're all perpendicular. How do you feel about that? Okay. You're all being very reserved. If it's not okay, stop me. Well, yeah, Jalen, I see your thumb. Okay, Laura. If there's anything you'd like to ask Nick, great, Kayla.
What does the bottom of the second row, like,
This
column of words, like after if?
If,
What is that word?
If I doesn't equal J.
Okay.
So if I and J are different, then BI dot BJ is 0. In other words, if I and J are different vectors, if BI and BJ are different vectors, you want their dot product to be 0. You want them to be perpendicular. So in R3, the vector I, sorry, we call the E1 of this class. The vector E1 1, 0, 0. So that's the vector pointing 1 unit out in the x1 direction. The vector E2, there's E1. Here's E2. 0, 1, 0. And E3 0, 0, 1 is an orthonormal basis. Orthonormal is kind of a long word, so we often abbreviate it ON. Sometimes without even the periods there. If I write ON basis, it means orthonormal. You can see it. I mean, you can see that each of these vectors, E1, which points directly out in the x1 direction, E2, which points directly in the x2 direction, E3, you can see that each of those vectors is length 1, and they're all perpendicular to one another. And you can see that from here. If I take the length of E1, it's just 1 squared plus 0 squared plus 0 squared, that's 1. The length of E2 is 1, the length of E3 is 1. And you can see that the dot product between these vectors is 0. So here's an example of an orthonormal basis in R3. It's certainly not the only orthonormal basis. So the usual orthonormal basis in R3, take your right hand, your index finger is pointing out of the blackboard, out of your page at you, that's E1. Your middle finger right here is pointing in the positive x2 direction, that's E2, and your thumb is pointing in the positive x3 direction, that's E3. And we're trying to, I mean, it's hands, they're not quite perpendicular on my hand, but on the blackboard they're perpendicular. Imagine them perpendicular. But I could just rotate this around any way I want and keep them perpendicular, and I have infinitely many different orthonormal bases. So let's ask the question. I guess I'll come over here. Is this an orthonormal basis for R3? Say B1 equals one half, 1 over root 2. B2 equals 1 over root 2, 1 over root 2, 0. Oops, sorry, I want that to be minus 1 over root 2. And B3 equals 0, 1 over root 2, minus 1 over root 2. Is that an orthonormal basis? we can start computing the length of the vectors. B1, length of B1 is the square root of 1/2 squared plus 1/2 squared plus 1/√2 squared. In other words, square root of 1/4 plus 1/4 plus 1/2. 1/4 plus 1/4 is 1/2, plus 1/2 is 1. That looks like it equals 1 to me. What about the length of the other two vectors? What's the length of B2? One over √2 squared is 1/2. 1 over minus √2 squared is 1/2. 0 squared is 0. Well, if that one has length 1, then this one certainly has length 1. They use the same 3 numbers to build it. So all these vectors have length 1. Let's make sure they're all perpendicular. B1 dot B2, let's start with B1 dot B2. That's going to be 1/2 times 1 over √2 plus 1/2 times minus 1 over √2 plus 1 over √2 times 0 so that's 1 over 2√2 minus 1 over √2 plus there we go. That equals 0 plus 0, which is 0. So B1 and B2 are perpendicular. Are B, say, 2 and B3 perpendicular? You take the dot product of B2 and B3 to get 0. That's not 0. So we were doing so well there for a while, but as it turns out, this is not an orthonormal basis because B2 and B3 are not perpendicular. The answer to the question is no. All these vectors do have length 1, and the first two happen to be perpendicular, but the second and the third are not. Let's do another one. go from R3 to R2. How about 3/5, 4/5, 4/5 minus 3/5. At least there are no square roots this time. And it's a smaller dimension, so there's fewer things to check. All you have to do is see whether those two vectors have length 1 and whether they're perpendicular to one another. Like the B1 is the square root of the length of, 3/5 squared plus 4/5 squared. That's the square root of 9/25 plus 16/25, 25/25. That's the square root of 1. That's 1. That's good. And the other one, since I use basically the same two numbers except I have a minus sign there, length of B2 also does 1. So these two vectors both have unit length. They both have length 1. And let's see if they're perpendicular. B1 dot B2 equals 3/5 times 4/5 plus 4/5 times minus 3/5. Oh, we have two terms there which are exactly the same except one has a minus sign. So that's definitely equal to 0. So the answer to this is a resounding yes. If we were to graph this, you can see that this is sort of an orthonormal basis. So three-fifths comma 4/5. So let me just mark these in fifths. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. There's -1. So 3/5 comma 4/5. 3/5 over on the x-axis, 4/5 up on the y-axis. And 4/5 comma minus 3/5. Oops. I guess I have to put -1 minus 1. So 4/5 minus 3/5 is over 4/5 on the x1 axis and down 3/5 on the y-axis. So there we are. And we just tested that those two vectors are length 1, and we just tested that they're definitely perpendicular. Does everybody understand what an orthonormal basis is and how to find out whether something's an orthonormal basis or not? Cool. Well, I hope you are asking yourself the question, one of the most important questions you could possibly ask yourself, always a legitimate question, why should I care? Why does it matter what, what these orthonormal bases are all about? What's the point? Let's review the main job of a basis, any basis. So let's let V be a vector space. And B1, B2, BK, be any, not necessarily orthonormal. Make this for if lowercase v is any vector in this vector space, then there exists unique scalars C1, C2, all the way up to CK, such that C1 times V1, V1 C2 times B2 plus all the way up to CK times BK is equal to that vector V. In other words, the main job of a basis is so that you can express any vector as a linear combination of the basis vectors. And you can do it in one and only one way. That's the main job of a basis, to be able to express all the vectors in the vector space as a linear combination of those basis vectors. In one and only one way. The fact that the basis vectors span, which they do because it's the basis, tells you that there's at least one way of doing that for every vector. The fact that the basis vectors are linearly independent, which is the other half of being in a basis, tells you that there's at most one way of doing that for every vector. So this is the main job of a basis. That's what bases do. That's their raison d'etre. That's what they do. That's why they're here. But finding C1, C2, up to CK can be a lot of work. Let's just do this. Let me give you a basis for, say, R3 and a vector, and we'll find C1 through CK. So, for example, let's let B be R3, and I'll give you a basis. How about the vector? I'll call this B1, B2, B3, where B1 is, let's say, 1, 1, 1. B2 is equal to, how about 1, 2, 3, and how about B3 is equal to 1, 3, 1, 3, 2. That'll do. So you can check that that's a basis. I'm not going to do it right now. Just you can take my word for it. Let's let V be four, 5, 7. And let's express V as a linear combination of B1, B2, and B3. In other words, find C1, numbers C1, C2, and C3 such that V equals C1 times B1 plus C2 times B2 plus C3 times B3. Find those numbers. Find these coefficients that go in front of the basis vectors. Okay, no problem. We'll just go all the way back to the beginning of the course. So V, which is 4, 5, 7. I'm going to actually put the 4, 5, 7. I'm going to move this V on the other side of the equal sign. I'm going to write the C1, B1 first. So C1 times B1, which is 1, 1, 1, plus C2 times B2, which is 1, 2, 3, plus C3 times B3, which is 1, 3, 2, equals V. 4, 5, 7. Well, I have a vector equation here. I've solved vector equations lots of times. The easiest way of doing it is to transform it into something else. I could turn that vector equation into a matrix equation. I could change that vector equation into a system of linear equations. But probably the easiest thing to write down is write this as an augmented matrix. 1, 1, 1, 1, 2, 3, 1, 3, 2, vertical bar, 4, 5, 7. And what do I have to do with that augmented matrix?
Row reduce it.
Yeah, row reduce it until you have, we know that this is the basis. We're going to end up with the identity matrix over here, and whatever the numbers are here, here, and here, once we row reduce it, those are going to be your C1, C2, and C3. So we have to row reduce. We can start. We could go, we already have a 1 there, so 1, 1, 1. I could go row 2 minus row 1, which is, let's see, 0, 1, 2. So let's see, 5 minus 4, I guess, is 1. And I could go row 3 minus row 1. So that's 1 minus 1 is 0. And 3 minus 1 is 2. And 2 minus 1 is 1. And 7 minus 4, I think, is 3. And I'll keep row reducing. So 1, 1, 1, 4. I need to get a 0 here. So 1, 1, 0, 1, 2, 1. I'm going to take row 3 and subtract off 2 times row 2. So 0, 2 minus 2 times 2 is 0. 1 minus 2 times 2 is negative 3. 3 minus 2 times 1 is 1. Now I have to get zeros above the diagonal. So let's see. Oh, first I have to get a 1 here. I forgot about that. So I'll take 1, 1, 1, 4, 0, 1, 2, 1, and minus 1/3 times row 3. So 0, 0, 1, minus 1/3. We can see our answers are going to have fractions in them. Now I have to get zeros here and here. So I can take row 1 and subtract off row 3. So 1, 1, 0. So that's 12/3 plus 1/3 is 13/3. I can take row 2 and subtract off 2 times row 3. That's 0, 1, 0. So that's 3/3 minus 2 times minus 1/3. So that's 3/3 plus 2/3 is 5/3. 0, 0, 1, minus 1/3. I guess we're just one step from being finished. We might as well finish. Let's see. Row 1 minus row 2. 0, 1, 0, 0. 13/3 minus 5/3 is 8/3. 0, 1, 0, 5/3. 0, 0, 1, minus 1/3. And so there's your C1 and C2 and C3. I'm sure those numbers were on the tip of your tongue when we started the problem. So in other words, that's C1, and that's C2, and that's C3. And we've expressed that vector as a linear combination of these 3 vectors. Was that a lot of work? I don't know. Row reducing a 3 by 3 matrix, not bad. Imagine if we were, instead of R3, in R10. So I would have given you 10 vectors instead of 3 vectors, and another vector, and said, express this as a linear combination of those. And you would have to row reduce a 10 by 10 matrix. Anybody want to do that? Me neither. Good, yeah, good thinking. Yeah, I don't want to either. So even though the job of a basis is to express any vector as a linear combination of the basis vectors, actually doing that, it can be a lot of work. Statement is perfect. Say B1, B2, all the way up to B, say N, is an orthonormal basis. So not only is it a basis, but all the vectors have length 1, and they're all perpendicular. It's an orthonormal basis for the n-dimensional vector space V. Now, of course, V has this dot product. So we taught, in order for orthonormal to make sense, in order for length and angle to make sense, we had to put a dot product on. Have this basis, and let's say little v is any vector in capital V. And of course, the main job of a basis is to be able to express any vector as a linear combination of these basis vectors. So there exist numbers, scalars, C1, C2, all up to Cn, such that C1 times B1 plus C2, C2 times B2 plus all the way up to Cn times Bn equals V. You can express any vector as a linear combination of the basis vectors. And we saw for a regular old basis how we have to do that. If we were in 10-dimensional space, we'd have to set up a 10 by 10 matrix and row reduce it. Lots of work. But for an orthonormal basis, it's easy to compute these C's. So C1 is nothing more than the dot product of the vector V with B1. C2 is nothing more than the dot product of the vector B of V with B2, and so on, all the way up to Cn. It's just the dot product of the vector V with the nth basis vector. That only works if B1, B2, all the way up to Bn is an orthonormal basis. These things are easy to compute. Even better, if all I wanted was C2, if I didn't need the rest of them, I could just do one computation. In the original case, if all I wanted was one of those numbers, I'd have to do most of the work for all of them. An orthonormal basis does the job of a basis, but easier, better. So let's take a look at an example. Say B is R2. We already determined that B equals B1, B2, where B1 is, what was it, 3/5, 4/5. B2 was 4/5 minus 3/5 is an orthonormal basis. Let's let V be 1, 1. Express B as a linear combination of B1 and B2. In other words, find C1 and C2 so that C1 times B1 plus C2 times B2 equals C. Well, there's two ways I could do it. I could either set up the augmented matrix, which isn't that hard actually, because it's only 2 by 2. 3/5, 4/5, 4/5 minus 3/5, vertical bar 1, 1, and row reduce until I had the identity over here. And then whatever numbers were over here would be my C1 and C2. It's just a 2 by 2 matrix. It's not that bad, other than the fact that there are fractions, which always makes things a little bit harder. Or I could just say C1 equals 3/5, 4/5, dot 1, 1. In other words, 3/5 times 1 plus 4/5 times 1. Or 7/5. And C2 equals, let's see, 4/5 minus 3/5 dot 1, 1. The order in which I dot them doesn't make a difference. So that's 4/5 minus 3/5. That doesn't have a vector symbol over top. Neither does this. They're scalars. So it takes a hard problem, it makes it easy. And this wasn't all that hard, but this is just as easy if you do it in 10 dimensions as it is in 2 dimensions, basically. Taking dot products is easy. Row reducing matrices gets hard. So a orthonormal basis does the main job of a basis, but better. Is that good? Great. Okay, great. Well, even better than I thought. So for those of you who are not in my 353 class, I will see you all on Wednesday. For those of you that are in my 353 class, I will see you in 7 minutes. don't forget that today we're going to talk about what's going to be on the final exam, and we're having lunch together.